Welcome to Math260. Our first lesson, Lesson 1, has to do with vectors. Well, what's a vector? Vector, there's several descriptions, both a geometric one and algebraic one, and we'll look at both. But to get the idea of the geometric one, consider the following example. Suppose I tell you there's a great party at Joe's house on Saturday night at 5 p.m. and it's real easy to get to. You just go 17.6 miles. What's the natural question that comes up? Which way? Which direction? Well, this is the idea of a vector. What a vector is, it gives me two things. It gives me a direction and a distance. The direction is which way the arrow points, and the distance is how long the arrow is. So we might call that vector u. And if I have another vector, it could point in a different direction and be of a different length. And this corresponds naturally with the way we give directions to people. That is, you go a certain number of miles in this direction, or for airplanes, you fly this compass direction for a certain number of miles. So vectors have a natural interpretation here in a geometric way. Now, when we want to add vectors, the idea is pretty simple. We can think about it as if I want to add the vector u and the vector v, the way I think about it is I first go this far in that direction and then go this far in the next direction. That means I start here, follow u, and then I follow where v takes me from there. Its directed distance. So the resulting vector, the total u plus v, is a vector that goes directly from the start point to the end point. U plus v. Like that. But what if I add v plus u? Well, following my definition, I first go along v's vector, and then starting there at the tip or the head of the arrow here, I now go in u's direction for its distance. And as we'll show later, I end up at exactly the same point. So not only is this u plus v, but it's also v plus u, and it takes me to the same place. We call this head-to-tail addition. Where I simply place the tail of the second vector on the head of the next one, and the result is the direct distance that takes me from the starting point to the end point. Now, there's also a way to multiply vectors. We think of multiplying a vector by a number or a scalar. What that does is changes the length of the vector. So let's look at that example. I'm going to erase this one. We'll take a new vector u that goes in some direction for some distance. What would it mean to multiply u by 2? Well, multiplying by a number means go in the same direction, but if I multiply by 2, I go twice as far. So that would be the vector 2u. The same direction, but twice the length, multiplying by 2. Or I could multiply by 1/2. Again, the vector would be the same direction, but half the length. And finally, what would it mean to multiply by a negative number? Well, if I multiply u by -1, what that means is go in along the same line in exactly the opposite direction, but the same length. And similarly, -2 times u would be in the opposite direction, but twice as far, etc. So this is the idea of scalar multiplication. It doesn't change the direction or the line that a vector lies on, it only changes the length. If it's positive, it grows or shrinks along the same direction. If I multiply by a negative number, it grows or shrinks along exactly the opposite direction, 180 degrees out. So this is the general idea of the geometric view of vectors. Now we're going to look at the algebraic view of vectors. Algebraically, I think of a vector as an ordered set of numbers. For example, there's we call a two-dimensional vector because it's two numbers. Now, how is this connected to the geometry? Well, we can think of this as the x and y components of the vector. So if I set up a axis system, the regular Cartesian plane, then the vector 3, 4 would mean I would go 3 in the x direction and then 4 in the y direction. So I'd end up here, and the vector would look like this, where its x component is 3 and its y component is 4. Now I can do vectors in any size. That is, I can make a vector that lives in three-dimensional space or in five-dimensional space. Etc. Now, how do we add vectors algebraically? Well, let's look at the example starting with the vector 3, 4, and we'll add another vector of the same length, a vector of length 2. So we'll add the vector minus 2, minus 3. Well, remember what it meant to add head to tail. I'd take this vector, and then I would follow the next vector. So to add them, I would have to start here and then go negative 2 in the x and minus 3 in the y. So I'd end up back here, and then the sum vector is simply the vector 1, 1. And arithmetically, it's easy to see how that works. I simply add the corresponding components. So to add the vector 3, 4 and the vector minus 2, minus 3, I simply add the corresponding elements. 3 minus 2 is 1, and 4 minus 3 is 1. So the addition of vectors, when I have them written in this coordinate form, I simply add the corresponding elements. What about vector scalar multiplication? Well, let's look at another example to do this. Again, start with a coordinate system. And I'll take the vector 2, 1. So I go over 2 and up 1. Up 1. There's my vector with coordinates 2, 1. If I multiply that vector by 2, it means I need a vector twice as long in the same direction. Well, that means I have to go twice as far in the x direction and twice as far in the y direction. So twice as far in the x direction is 4, and twice as far in the y direction is 2. So 2 times the vector 2, 1 gives me the vector 4, 2. Same direction, but twice as long. And notice how I accomplish it. I simply take the number and multiply it by each element. 2 times 2 is 4, and 2 times 1 is 2. If I want a vector that's half the length, that is 1/2 of 2, 1, I simply multiply each element by a half. 1/2 of 2 is 1, and 1/2 of 1 is 1/2. So that would be the vector 1/2 of the original vector, and that would look like this. So to do scalar multiplication of vectors, I simply take the scalar and multiply it by each element, and that gives me the resulting vector. So that's the idea of algebraic vectors versus geometric vectors, and you can see they're tied together this way, but the beauty of the algebraic approach is I don't necessarily have to think about vectors as coordinates, as having anything to do with geometry. For example, I might consider the following vector. That might be used to encode the grades of a particular student on the 4 exams in a class, 87 on the first, 93 on the second, 82 on the third, and 78 on the fourth. It collects them into a group for that student. I give the student's test vector. And similarly, we can use vectors to represent all kinds of things. I might have a vector v that's a chemical representation. This is how many carbons, this is how many hydrogens, this is how many oxygens. This could be a vector that represents the chemical C6H12O6, etc. So when I use just the algebraic look at vectors, they can represent all kinds of things, not necessarily having a geometric idea. So let's finish up today with just a couple of examples that we can work. Let's take vectors in 3-dimensional space. There's the vector u with coordinates 2, -4, 5, and the vector v with coordinates -3, 4, and 2. So first of all, let's do u plus v. Now I simply add the corresponding elements. 2 minus 3, or 2 plus -3 is -1. 4 minus 4 plus 4 is 0. And 5 plus 2 is 7. So there's the vector representing the sum u plus v. How about u minus v? Well, what that really is u plus -v. But the arithmetic works the same. I take the first element in u and subtract -3. 2 minus -3 is 5. -4 minus 4 is -8. And 5 minus 2 is 3. So there's u minus v, or we can think of this as the same as u plus -1 times v. And how about scalar multiplication? Our last example. How about 3 times v? Well, I simply take each element of v and multiply it by 3. 3 times -3 is -9. 3 times 4 is 12. And 3 times 2 is 6. So, example of vector addition, vector subtraction, which is really vector addition with a -1 is my scale factor, and scalar multiplication of vectors. So this is the basic idea of vector arithmetic, how to add vectors and how to scale vectors, both algebraically, using arithmetic, and geometrically.